All right. I hope you guys are doing well today. I'm still trying to sort out exactly what it is that I'm going to do about the issues with Respondus. But I just want to be very clear here that I am certainly not going to penalize any of you guys. Um, or like what I mean by that specifically is I'm going to give you an opportunity to make up those points that you may have missed because the computer program wasn't correctly displaying the circuits. Still haven't decided what I'm going to do, but everybody will have an opportunity to improve their grade for sure. So before we jump into today's lecture, does anybody have any questions about anything?
Could we possibly go over number two on homework 10?
Homework 10, number 2. Absolutely. Let me pull that up on my other computer so I can see what that is. All right. So, goodness. Homework 10, number 2. Um, I'm only going to work part A, which is finding the Thevenin equivalent circuit, because once we know that, part B is incredibly simple. So the circuit that we're given is this guy right here. We have a 20-volt source connected in series to a 40 ohm resistor. Then here we have a 200 ohm resistor, a 100 ohm resistor. Here we have a dependent source that is 1.5 IY, where, oh, excuse me, it's I1. Well, I'm just going to call it IY. This is the current IY that controls that guy. And then lastly, over here to the right is our set of terminals. So, let's solve for the Thevenin voltage first, okay? So the Thevenin voltage is going to be the voltage drop across that open circuited set of terminals here. And we're told in the problem statement that it says, assume the voltage source has a positive polarity on top, which means we're finding VTH with a positive polarity on top. So for this particular circuit, because I'm trying to find a voltage, I'd probably use nodal analysis here. Mesh wouldn't be bad by any stretch of the imagination, but we'd have to do extra work at the end to actually solve for VTH, whereas if we use nodal, we're going to get it directly. So that's how I'm going to go. So my controlling, actually, let me define my nodal voltages. So here's A, B, and C. So my controlling variable, IY, is just going to be VB over 200 ohms. I'm going to have a voltage relationship equation that is 20 volts is equal to VA. And now I'm going to have to write a KCL equation at node B and a KCL equation at node C. KCL at node B is going to look like VB minus VA over 40 ohms plus VB over 200 ohms plus VB minus VC over 100 ohms is equal to 0. And then lastly, KCL at node C is going to look like VC minus VB over 100 ohms minus 1.5 IY is equal to 0. I think the easiest substitution for us to make would just be to say that VA is equal to 20 volts, which would only impact that single equation. So here's equation 1, 2, and 3 that I'm going to throw into my system solver, where my variables are going to be VB, VC, and IY. So I'm opening up my system solver right now. So in my first equation, my coefficient for VB is 1 over 200. My coefficient for VC is 0. My coefficient for IY is -1 when I move it to the other side of the equal sign, and my constant term is 0. In my second equation, my coefficient for VB is 1 over 40 plus 1 over 200 plus 1 over 100. My coefficient for VC is -1 over 100. And my constant term is going to be positive 20 over 40 when I move it to the other, oh, excuse me, my coefficient for IY is 0. And now my constant term is going to be positive 20 over 40. In my last equation, my coefficient for VB is -1 over 100. My coefficient for VC is positive 1 over 100. And my coefficient for IY is -1.5. My constant term is 0. So solving this, I get VB is equal to 200 over 9 volts. VC is equal to 350 over 9 volts. And IY comes out to be 1/9 of an amp. And our Thevenin voltage, VTH, is just going to be the exact same thing as VC, which will be 350 over 9 volts. Just so that everybody's clear on why VTH is equal to VC, the positive polarity terminal of our voltage VTH is at node C, and the negative polarity terminal is at our bottom node, which is ground. So now we have a choice. We can either solve for I Norton, and then use the ratio of V Thevenin to I Norton to solve for VTH, or excuse me, to solve for RTH, or we can use a test source method in order to solve for RTH directly. I'm actually going to wind up doing both just so that we can kind of use it to check our work and also to give you guys a little bit more practice using the test source method. So let's find our Norton current next. So we're essentially going to be working with the same circuit, except that my terminals are now going to be short-circuited. So here's my 20-volt source, 40 ohm resistor, 200 ohm resistor, 100 ohm resistor, 1.5 IY. Here's IY. And now I'm short circuiting my terminals over to the right. Like so. And my Norton current is the current that's flowing down through this short. So to solve for the Norton current here, I think the easiest way to do this is going to wind up being mesh analysis. So let's make this mesh 1, this guy mesh 2, and this guy mesh 3. Our controlling variable relationship is going to be IY is equal to I1 minus I2. Our current source relationship is going to be 1.5 IY is equal to I3 minus I2. And now we're going to have a KCL equation around mesh 1 and a KCL equation around super mesh 2, 3. So we're going to do the super mesh equation first. So that's going to look like 200 ohms times I2 minus I1 plus 100 ohms I2 is equal to 0. Around mesh 1, we're going to have negative 20 volts plus 40 ohms I1 plus 200 ohms I1 minus I2 is equal to 0. And I'm going to substitute I2 minus, excuse me, I1 minus I2 in for IY. So I'm just taking this stuff, plugging it in here. And I'm going to go ahead and rewrite that equation real quick, right? So I'm going to have 1.5 I1, excuse me, and then I'm going to have minus 1.5 I1, or excuse me, I2, but then I also have this minus I2 on the other side. So when I add that over, that's going to leave me with minus 0.5 I2. And then when I move I3 over to the left-hand side, that's going to look like minus I3 is equal to 0. And so now I have 1, 2, and 3 equations to solve for. So putting this into my system solver, in my first equation, my coefficient for I1 is 1.5. My coefficient for I2 is negative 0.5. My coefficient for I3 is negative 1, and my constant term is 0. In my second equation, my coefficient for I1 is negative 200. My coefficient for I2 is 200 plus 100. My coefficient for I3 is 0, and my constant term is 0. And in my third equation, my coefficient for I1 is 40 plus 200. My coefficient for I2 is negative 200. My coefficient for I3 is 0, and my constant term is 20. Solving this system, I get I1 is 3/16 of an amp. I2 is 1/8 of an amp. And I3 is 7/32 of an amp, where our Norton current, I Norton, is just the same thing as I3 is 7/32. So putting these results together, we should find that our Thevenin resistance is just VTH over I Norton, comes out to be 350 over 9 divided by 7/32. I can't do that in my head, so I'm throwing that into my calculator. And I wound up getting 1600 over 9 ohms. So the last thing that I would like to do here is just use a test source method to verify that that is correct. Okay. So I need to be dealing with a dead network. So I've turned off my independent voltage source. Here's IY again. And for this circuit, our choice of test source doesn't particularly matter. It's not going to make anything any easier regardless of which kind of source we use. So I'm just arbitrarily going to use a 1 volt source over here. And I'm trying to find this test current I test, and I'm going to do that using mesh analysis. So here is mesh 1, 2, and 3. Our controlling variable relationship is going to look like IY is equal to I1 minus I2. Our current source relationship is going to look like 1.5 IY is equal to I3 minus I2. And if I substitute in this relationship into here, I should get the exact same result as I got earlier. So that's going to look like 1.5 I1 minus 0.5 I2 minus I3 is equal to 0. When I apply Kirchhoff's voltage law around mesh 1, I'm going to have 40 ohms times I1 plus 200 ohms times I1 minus I2 is equal to 0. Sorry, my penmanship is getting crappy. And when I apply KCL around my super mesh, I'll have 200 ohms I2 minus I1 plus 100 ohms I2 plus 1 volt is equal to 0. So here is equation 1, 2, and 3. This system is going to be very similar to the one that we just solved to find I Norton, so I'm just going to update that guy. So my first equation didn't change at all. My coefficient for I1 is 1.5, coefficient for I2 is negative 0.5, coefficient for I3 is negative 1, constant term is 0. In my second equation, my coefficient for I1 is 40 plus 200. My coefficient for I2 is negative 200. My coefficient for I3 is 0, and my constant term is 0. And in my third equation, my coefficient for I1 is negative 200. My coefficient for I2 is 200 plus 100. My coefficient for I3 is 0. And lastly, my constant term is minus 1. So solving, I got I1 is negative 1 over 160 amps. I2 is negative 3 over 400 amps. And lastly, I3, I got to be negative 0.005625 amps. It didn't give me a fraction. From here, our Thevenin resistance is going to be V test over I test, which is going to be 1 volt divided by I test. I test is simply negative I3. So that's going to give us 0.005625 amps here. Which comes out to be 1600 over 9 ohms. So we did the VTH and the I Norton bit correctly, obviously, since we got the same value for RTH both ways. So probably overkill, but I just wanted to show you guys the different ways that you could wind up getting both of the parts. For what it's worth, if you solve for the Norton current and the Thevenin resistance, you could have used those two quantities to back solve for VTH without ever actually calculating it. Realistically, as long as you have any two of the quantities, you can get the third one as long as you've found those two quantities correctly. Okay, was that a sufficient explanation, Colin?
Yes, sir.
Okay, any other questions? All right, so let's jump into today's topic, which is um, inductance and inductors. So when we talked about resistance, gosh, almost a month ago at this point, we started by talking about resistance and what it means first, and then we moved towards resistors and what they do. We're going to go in the opposite path here. So I'm actually going to talk about what an inductor is first, and then from our look at that, we're going to figure out what inductance is actually doing in a circuit. So in order for us to have any idea of what an inductor is doing, we need to very quickly introduce some electromagnetic field theory concepts. Once again, I fully understand that the overwhelming majority of you all have not taken Physics 202. So this is probably going to be new to you. You'll unfortunately have to take it on faith that I am correct, but for what it's worth, I am. So I want to start with a simple thing, which is just a section of current carrying wire. Okay. So let's say that we have a section of wire that is part of some larger circuit. And we will say that some DC current I is flowing through the wire. Okay. Well, whenever you get around to taking your electromagnetic field theory classes, and everybody I think has to take Physics 202 at some point, what you'll learn is that you can use what's called the right-hand rule in order to determine the direction of magnetic fields. So essentially, any time that we have current flowing around any path, the movement of electrons is going to cause a magnetic field to occur. And the right-hand rule tells us that if our thumb is in the direction of current flow, then our fingers on our right hand will curl around and tell us the direction of our magnetic field. So if you put your hand up in the air, your right hand up in the air with your thumb directed to the right, you should see that your fingers are curling around such that above the imaginary wire that you're holding in the palm of your hand, your fingers are pointed out, and below the imaginary wire, your fingers are pointed in. So what we would see are essentially field lines that would look something like this. So what I'm trying to represent here is kind of like the head of an arrow directed out of the page. And down here below, we see the tail of that same arrow entering the page. Magnetic field lines form closed loops. They have to. There is no such thing as a magnetic monopole. We only have magnetic dipoles, and that means that those loops have to be closed. Okay. So Now, as a simple experiment, let's say that instead of a long straight section of wire, we have a circle of wire that's carrying some current. Okay? So bear with me here while I attempt to draw a circle. So here's our circle of wire. And let's say that our current is flowing clockwise around our wire, like so. So in a situation like this, the right-hand rule can also be used, okay? So essentially, now if our fingers curl around in the direction of current flow, then our thumb is going to point in the direction of the field. So if we curl our fingers around such that on our right hand, such that they're curled clockwise, we should see that our thumb is actually pointed down. Okay. So what that means is that inside of our circular current carrying wire, we're going to find that our field is directed down into the page, and outside of our current carrying wire, our field is going to be directed up out of the page, like so. So now I want to introduce you guys to an inductor. Okay. So I'm going to start by drawing what's called a solenoidal coil. So the first thing I'm going to draw is kind of like a form for us to wrap our coil around. Okay, so it'll be something akin to this. So I've got this cylinder, um, and this is representing the core material of our element. And around this core, I'm going to wrap a wire. Okay. So if I pass some current I of t down the wire, we can think of this coil as just a stack of those current carrying rings. Okay. So if our fingers are wrapping around in the direction that current is flowing, what we should find is that we're going to have magnetic field lines that are going to be oriented like this. So directly along the axis of our inductor, they're going to be vertical. But as we get slightly away from the axis of symmetry of our inductor, they're going to be vertical, but then they're going to turn back around like so. And the same thing is going to happen on the opposite side as well. So let's talk about why we coiled the wire like this. Okay. So if we coil the wire like this, what we're doing is we are creating a lot of magnetic field lines inside our core material, right? So for every single turn of our coil, we're creating some amount of magnetic field. And by stacking lots and lots and lots of turns on top of each other, we're making that field stronger and stronger and stronger inside of our coil. Okay. So what we are actually doing is creating some sort of energy storage element because it takes energy in order to sustain the field that's being generated by our current. And if we were to turn that current off, it would release that energy back into the circuit. Okay. So that's all an inductor really is it's just a coil of wire whose job it is to store energy in the form of a magnetic field. Okay. Now, this solenoidal coil inductor um, has a little bit of a problem in as much as it tends to lose energy because we allow it to spread out on its return path, right? So as it flows out of the top of our inductor, and makes its circular path back towards the bottom to complete those loops, it spreads out. So we're essentially just losing some energy into the air. Okay. So in order to alleviate this, instead, we might use what's called a toroidal coil inductor. And if any of you guys have ever opened up your power supply for your computer or any type of electronics, you've probably seen toroidal coil inductors before. Okay. So I'm going to attempt to draw one here. So once again, we've got our core material. In this case, it's going to be a donut-like shape. So this is going to be the interior of that donut shape. And then I'm going to attempt to draw a concentric circle around it, like so. And what we're going to do now is much like we did with the solenoidal coil inductor, we're going to wrap a wire around this donut. So that should look something like this. Again, this is a toroidal coil inductor. So let's say that our current I of t is flowing in this direction. And so what this toroidal coil inductor does is it effectively completes what would commonly be called a magnetic circuit, but we're not going to really dive into that in this class literally at all. But essentially, because it doesn't have any air gap, it shouldn't have any losses. So what we'll find is that our magnetic field lines still get confined, so that we have lots of coils, so that we have large amounts of magnetic field in our structure. But now our magnetic field just circulates around inside of this core material, and we don't have any losses to deal with. Okay. So this is a better inductor for most applications, loses much less energy out into the air. Still going to lose some energy because it takes a little bit of energy in order to magnetize the core material and all of that kind of good stuff, but we're not really going to concern ourselves with that too much. Okay. So these are the two types of inductors that you might see implemented in physical circuits. Okay. You'll probably see significantly more toroidal coil inductors than you do solenoidal coil inductors, um, for the reasons that I've talked about, lower losses and things like that, but both are used very regularly. Okay. So let's now talk about how we would represent these inductors in a circuit. Okay. So our schematic symbol is going to look something like this. So our inductor is a two-terminal element, just like our resistors and our voltage and current sources. Um, and we draw our symbol like this. So what it is literally just a coil of wire. That's all that the symbol represents. And that's because in its most basic form, that's literally all an inductor actually is just some coil of wire. Okay. So our inductor is going to obey the passive sign convention, which means if I choose to put the positive polarity terminal for the voltage drop across our inductor over here on the left, so let's call this VL as a function of time, and current is flowing into the positive polarity terminal, let's call this IL as a function of time, then we would say that our inductor is absorbing power or absorbing energy. If the current was flowing into the negative polarity terminal, then we would say that our inductor is storing power or supplying power or supplying energy. Okay. So now let's get into the math behind this. Okay. Um, so I'm going to go ahead and put the symbol for inductance here, L, on our schematic symbol. Okay. So just like R means resistance, L, for whatever reason, is used as the symbol for inductance. Okay. Now I'm going to introduce the current and voltage relationship for an inductor. And again, this has some background electromagnetic field theory that you guys aren't going to be super aware of, so I'm just going to gloss over a lot of it. But essentially, what we have is a circuit element whose operation is defined by Faraday's law of induction. Okay. So Faraday's law of induction says that an electromotive force, that's script E, is going to be equal to the change in magnetic flux with respect to time. So what we're going to do is we're going to take this relationship and convert it into a more understandable circuit form. Okay. So first, let's talk about an electromotive force. Okay. So that's what that fancy script E means, is electromotive force. And an electromotive force is just a force per unit charge that pushes charge around. Well, that is literally the exact same thing as a voltage. So that fancy script E is just going to be replaced by voltage as a function of time. Okay. Now, let's get into this whole change in magnetic flux thing. Okay. So magnetic flux is just the total amount of magnetic field. So it's just magnetic field per unit area. Okay. So if we put a time varying current into our inductor, we will induce a time varying flux. And that flux will change at the exact same rate as which our current changes. So over here on the right-hand side, I'm going to put the derivative of our current with respect to time. Okay. So the thing that's relating our flux to our current is actually that inductance L. Okay. So we can define inductance as the property of an electrical component that quantifies its ability to induce a voltage due to a change in electric current. So essentially, the larger the L is, the larger the induced voltage will be for a given rate of change of current. What we're going to see a bit later on is that this inductance L is also related to how much energy can be stored by the element as well. Okay. So now let's look at the units of inductance. Okay. So if we rearranged our expression, I'm going to do this in blue since we're going to play around with things here. We could essentially say that our inductance L is going to be our voltage V of t divided by the derivative of our current. So before I start playing around with the units and stuff like that, is everybody okay with that small amount of algebra I've done to rearrange and solve for L? All right. So we know that voltage is measured in volts. And now we just need to figure out what the derivative of current is going to look like. But I think that that should be pretty easy because we know that current is measured in amps. And so if we're taking the derivative of current with respect to time, that should give us amps per second. And so we could rewrite this as a volt second per ampere. And this is what is commonly called a Henry. So lowercase h when we're spelling the unit out, capital H when we're showing that unit on a schematic diagram or something like that. Okay. So 1 Henry is defined to be a volt second per ampere. For what it's worth, we could also say that it is an ohm times a second, since a volt per amp is an ohm. Okay. So 99% of the time, anytime I see Henry, I'm just going to replace it with those fundamental units of volt seconds per ampere to make sure everything works out okay. All right. So that is our um, unit of inductance and broken down into its base units. So before I move on from here and we start discussing our relationships for the inductor, does anybody have any questions? All right. So let's talk now about inductor relationships. So the first relationship that we're going to talk about, I've actually already given you guys, and that is the um, voltage drop across an inductor is equal to inductance times the derivative of the current flowing through the inductor. So this is relationship number one. Okay. I'm going to put a box around it because it is very important. And for what it's worth, you are expected to learn this relationship, or really you're expected to memorize it, but I think it would be better served if you were to learn it for your upcoming exam. Okay. So this is the fundamental relationship that is governing the behavior of an inductance. And we can kind of look at this relationship and make some observations about how it is going to behave in some specific situations. Okay. So I'm going to draw a little picture here. So let's say, just for the sake of argument, that I have a 1 Henry inductor. This is going to be the voltage drop across my inductance. And this is the current flowing through my inductance. Okay. So let's look at this first case. Okay. So if the current flowing through my inductor, so here's IL of t, and here's t. So let's say that the current flowing through my inductor is just some constant value. Okay. What should the voltage drop across my inductor be? Anybody care to venture a guess?
Wouldn't it be zero because when you take the derivative of a zero slope or of a zero slope, it's just zero?
Exactly right, Colin. Thank you. So if our current isn't changing, then we cannot induce a voltage drop across the terminals of our inductor. So essentially what we'll see is that for any constant current, the voltage drop across our inductor is just zero. In other words, in a DC circuit, inductors can be treated like a short circuit. Okay. So I'm saying that inductors can be treated like a short circuit for two reasons. Okay. First, we know that the voltage drop across a short circuit is always zero. And we've just shown that for a constant current, the derivative of the current is zero, and so the induced voltage must also be zero. And also, in DC, our coil of wire is just going to look like a piece of wire, which we treat pieces of wire in this class as if they are short circuits, okay? So this is our first relationship, or the first little kind of thing that we can glean from this mathematical relationship. Voltage is equal to inductance times the derivative of the current. Now let's go to the complete opposite extreme, okay? So here's going to be case number two. So let's say that I have a situation, something like this. So here's IL of t. And let's say that our current is zero, and then it instantaneously changes to have some finite value, and then instantaneously drops down like so. If I were to express this as a piecewise function, and I'll do this over here to the left, just so that we can make sure we're all catching the same thing. Let me call this point in time T1 and this point in time T2. I would say that my current is 0 amps for 0 is less than T is less than T1. And I'm going to put T1 minus. So that means I'm just approaching T1 from the left. Then if I give this a value of, let's say, 1 amp, it would be 1 amp from T1 plus, so that's just approaching T1 from the right, is less than T is less than T2 minus, and then we would have 0 amps again for T greater than T2 plus. Okay. So we have an instantaneous change in our current through our inductor from 0 amps up to 1 amp. Okay. So what do you guys think our voltage would look like in that case? So what's our derivative at T1? Anybody care to venture a guess? So I would say that it is infinitely large. Okay. So the reason why I'm saying that it's infinitely large is because our rise is 1 amp, but our run is 0 seconds, right? Because it instantaneously changed from 0 amps up to 1 amp. So what we would actually see is that while our current is constant, let me label T1 and T2 here. And it'll be obvious why I put T2 on top in a second. So while our current is constant, our voltage is 0. But then we see this infinite slope essentially. And so what that's going to look like is an impulse. So our current, excuse me, the voltage drop across our inductor is going to jump up, and it's actually going to be infinitely large at this point in time. Then it's going to fall back down. And then at T2, our slope is negative infinity because our rise is negative 1 amps divided by that 0 seconds. So now we're going to have a negative impulse, and then it's instantly going to jump back up to 0 and stay 0 because our current is once again constant. So does anybody see a problem with this?
How can you have infinite voltage?
That is indeed the problem. Thank you for that, Joseph. So, an infinite voltage means that there has been an infinite transfer of energy, right? Because voltage is the amount of work done or the energy required to move charge around our circuit. So, if the current in our inductor were to change instantaneously, it would cause an infinitely large voltage to appear. Well, that can't happen, right? So essentially, if the current flowing through an inductor changes abruptly, we accidentally break the laws of physics. Now, this isn't something that we could ever truly replicate in real life, right? Because it's impossible for us to change the amount of current that's flowing through any element instantly. It takes time for things to change and stuff like that. But what we're going to do is we're going to come up with another little kind of rule here. And we are going to say that the current, that does not look like a good second R there. Through an inductor cannot change abruptly. And I'm going to put in parentheses here, IL at T minus must be equal to IL at T plus. Okay. So this essentially just means that the current flowing through an inductor must be a continuous function in time. Okay. So any change has to occur over some amount of time. It could be nanoseconds, but it still takes some amount of time for that change to occur. Our next large topic in this class is what's called the transient analysis of RL and RC circuits. And this statement, the current through an inductor cannot change abruptly, will be used to explain how our inductors are behaving as our system undergoes changes. Okay, so this isn't something that we're going to see again for another couple of class meetings, and then we're going to see it over and over and over again. Okay, so before we move on from this derivative-based relationship for current and voltage through the inductor, that's this relationship number one. Does anybody have any questions or comments or anything? All right. So for our second relationship, we're actually just going to take that first one and we're going to manipulate it a little bit. Okay. So let's start with VL is equal to L di by dt. And what I'm going to do is I'm going to multiply both sides through by a factor of dt. So if anybody has a math minor, you're about to witness some real engineering math here, so I hope it doesn't hurt your feelings too much. So I multiplied both sides through by a factor of dt. And now, because I'm an engineer and not a mathematician, I'm going to say that those guys are going to cancel each other out. And what I'm going to do now is rearrange a little bit. Okay. So I'm going to have the derivative of current here on one side of the equal sign. And then I'm going to have 1 over L times my voltage times dt over here on the right. So I've just algebraically moved things around here. And now what I'm going to do is I'm going to take the integral of both sides. So if I integrate this side and I integrate this side, what I should wind up getting is, so the integral of the derivative of my current is just my current. 1 over L is a constant, so I can take it outside the integral. And I'm left with the integral of my voltage with respect to time. Now I'm going to throw some limits on this integration. Okay. So I'm going to start my integral at t is equal to negative infinity. Okay, so this is the beginning of time or whenever the inductor was first created, whatever we want to call it. And I'm going to integrate up to some point in time t that I am interested in. Okay. So while this is correct, it's kind of unwieldy because essentially we have to know what the inductor was doing in the past in order to make this work. So instead, I'm going to choose to rewrite this integral as 1 over L times the integral from T naught to T of VL dt, and then plus, and this is happening outside the integral, IL at T naught. So this term right here is what's called an initial condition on the inductor current. So essentially, what it means is that in some sense, an inductor has memory. So what I mean by that is that what the inductor's current is valued at in the present is dependent on what its value was in the past, represented by this initial condition. Okay. So this is used, let me think about this really quickly. Let's work an example. I think that'll be the easiest way to understand what's going on here. Okay. So let's say that we have a 3 millihenry inductance. Here is the voltage drop across the inductor. Here is the current flowing through the inductor. And let's say that the voltage drop across the inductor, VL of t, is represented by the following relationship. So let's say that it is 5 volts for all time less than 0. And then it's going to be 5e to the minus 10t volts for all time greater than or equal to 0. Let's also say that the value of the inductor current at t is equal to 0 is 1 amp. Okay. So if we wanted to find out what our inductor current is at, let's say, t is equal to 2 seconds, then what we would need to do is integrate our voltage at the appropriate time and then also include that initial condition, because the past values of the inductor current are important. So putting all of this together, we have IL of 2 seconds is going to be equal to 1 over L times the integral from T naught to 2 seconds of VL with respect to time plus IL at T naught. All right, so first thing I'm going to do here is I'm going to do this 1 over L bit, right? So I have 3 millihenries, so that's 3 times 10 to the minus 3. So that gets rid of my milli. So now I just have henries. A henry is a volt second per ampere, so that means I'm going to have volt seconds down here and an ampere up top, like so. So this part right here represents my 1 over L. Okay. Now getting into my integral. So T naught is the time at which our inductor current was a known quantity. Well, we're told that the current flowing through the inductor at t is equal to 0 was 1 amp. So that means T naught is simply 0 seconds. Now I'm going to integrate out to 2 seconds. My inductor voltage at t is equal to 2 seconds is given by 5e to the minus 10t volts. And then out here, I need to add my initial condition, which is 1 amp, like so. I know that technically we all have calculators that can do this, but I want to make sure that you guys can follow the units as well. Okay. So I'm going to do this math by hand here. So I've got my 1 amp over 3 times 10 to the minus 3 volt seconds. Another thing I can do is I can pull that 5 volts out. Right? So pulling that 5 volts out of the integral is going to do something like that. And I can see, I think very easily that this volt cancels this volt. So now I'm left with something that's measured in amps per second. Okay. So how do I take the integral of an exponential function? So there's like a whopping 4 or 5 different functions that I expect you guys to be able to take the derivative of and the integral of, and an exponential function is one of them. So for what it's worth, I'm going to show you those relationships over here to the right because we're going to see them very, very frequently over the next several class meetings. Okay. So the derivative of e to the alpha t is alpha e to the alpha t, and the integral of e to the alpha t dt is 1 over alpha e to the alpha t plus c. Okay. So in this case, my alpha is negative 10. Okay. So what that means is that when I integrate that guy, I'm going to pull down a factor of 1 over negative 10. Now, because the exponential function has an argument that is unitless, meaning that negative 10 times t needs to not have any units. If t is measured in seconds, then that implies that negative 10 is measured in per seconds. Okay, so that's where this seconds to the negative 1 is coming from. Okay, and what we'll see is that this seconds to the negative 1 in the denominator cancels this seconds here, leaving us with just amps in the numerator, which is exactly what we should expect because we're trying to find a current. Okay. So now I've pulled down my 1 over alpha. So now I'm going to have just e to the negative 10t evaluated at 2 seconds and 0 seconds, like so. So let's play around with this just a little bit, right? So I have in my numerator 1 times 5, and then my denominator, I have 3 times 10 to the minus 3 times a factor of negative 10. So this is going to look like negative 500 over 3. Now I'm going to have e to the minus 10 per second times 2 seconds minus e to the negative 10 per second times 0 seconds. Okay. So that's going to look like negative 500 over 3. Sorry, that should be amps there. E to the negative 20 good God, is a really tiny number. I should have used a different thing. That'll be fine. And then e to the 0 is just 1. So that'll be minus 1. So this is going to wind up looking like 500 thirds of an amp times 1 minus E to the minus 20 is, excuse me, and I forgot to add +1 over here and +1 over here, so I'll do +1 amp over here as well. Anyway, sorry for forgetting the initial condition there. That is very important. But I just wanted to show you guys how the units wind up working here. So hopefully this example didn't actually wind up confusing you further. All right. So I'm going to come up here just really quickly. I'm going to call this relationship number 2. Okay. So this is our second inductor relationship. Our third inductor relationship is going to be for power. Okay. So the power absorbed by an inductor, by definition, will be the product of the voltage drop across the inductor and the current flowing through the inductor. But since the voltage drop across the inductor can also be expressed in terms of inductor current, this could be rewritten as L times inductor current times the derivative of inductor current with respect to time. That's literally just directly substituting in that equation 1 in for the VL as a function of time here. So this is relationship number 3. Okay. For what it's worth, I would say 95% of the time, I wind up just using the V times I relationship. Okay. It is very, very rare that I do L times the current times the derivative of the current. I usually just find the voltage, find the current, multiply them together, call it power, and I'm done. I personally find that much easier, and there's usually a little less, well, I guess it's really the same amount of calculus, but there's less opportunity for me to make a dumb mistake. So that's why I prefer to just do V times I. But anyway. The last relationship that we're going to talk about is the energy stored by our inductor. Okay. So as we talked about on our second class meeting, energy is simply the integral of power. Okay. So we could say that energy is the integral of PL as a function of time with respect to time. And this is one of the few places where I'll wind up actually using that relationship, right? The L times I times the derivative of I with respect to time. So what I'm going to do now is I'm going to substitute that in, and I'm going to go from negative infinity to t here on the boundaries of my integral. Okay. So this is the total energy stored by the inductor up until the point in time we're interested in. So if I substitute in my power relationship, I'm going to wind up having negative infinity t, here's L I di by dt, and then here's another dt. And once again, I'm going to say that that dt in the numerator cancels this dt in the denominator. So now instead of integrating with respect to time, I am essentially integrating with respect to inductor current. Okay. So since I've changed my variable, I need to change my bounds. So down here, I'm going to have IL at negative infinity. And up here, I'm going to have IL at t. And I have L, IL, D, IL, like so. So I know that this looks a little confusing, but essentially what I'm doing is this integral. So I'm integrating from something to something else. We'll sort that out in a second. But I have some constant, so I'm just going to call that constant, let's just leave it as L. IL of t is my variable. And then now I have the derivative, so that's that. Well, I can take that L and move it outside the integral. So I would have L times the integral of x dx. Well, the integral of x dx is just x squared over 2. Okay. So that's going to look like L times IL of t squared over 2 evaluated at IL of t and IL at negative infinity. Sorry, I drew that so shittily. We're going to make an assumption here, and we're going to say that the current that was flowing through the inductor at the beginning of time was 0 amps. And so what that allows us to do is say then that the energy stored by the inductor is actually just going to be 1/2 times the inductor value times the current flowing through the inductor at our time of interest squared. So this is our fourth and final inductor relationship. Energy is equal to 1/2 Li squared. Okay, so I have one more small thing that I want to talk about related to inductors. But before we get to that, I know I've hit you guys with a lot of relationships here. Realistically, understanding where they came from is significantly less important for you guys as to being able to apply them. So we essentially just have 4 equations in total. Okay, so I want to recap things really quickly. If we go back up here to equation 1, this is how we find the voltage drop across an inductor when we know what the current is doing. So that's what equation 1 is used for. Equation 2 is how we find the current flowing through the inductor when we know what the voltage is doing. Okay, so if the voltage is a known quantity, we can use this guy to solve for current. Equation 3 is just finding power. So we need to know both voltage and current to do it the easiest way, in my opinion. And then lastly, equation 4 is just energy. So the energy stored by an inductor is dependent on not only the inductor value itself, but also the square of the current flowing through the inductor at a given point in time. Okay. So those are our 4 equations in a nutshell and what they're used for. So before we move on, I'll reiterate, does anybody have any questions, comments, or concerns that we need to address before we talk about our next small topic here? All right, so the last thing that I want to talk about for today is how we can combine inductances in circuits where there are multiple inductors to deal with, okay? So I'm going to start by looking at inductors in series. And hopefully, if you guys are catching what I'm throwing, we won't have to do a bunch of extra calculus to talk about what happens when we have inductors in parallel. We can just intuitively understand what's going on. So starting with inductors in series, this is going to look extraordinarily similar to what we did when we had resistors in series. Okay. So here I've got some inductance L1. Here's some inductance L2, all the way out to some inductance L sub n, like so. I'm going to call this voltage VL1, this voltage VL2, and this voltage VLN, like so. And I'm going to say that the total voltage drop across all of my inductors connected in series is going to be some voltage V of t. And the current flowing through all of my inductors in series is going to be I of t. And obviously, because they're all in series, they all have that same current I flowing through them. So if I were to apply Kirchhoff's voltage law to this system, what I would find is that my total voltage V of t is simply equal to the sum of all of the voltage drops across those individual inductors. So that would be VL1 plus VL2 all the way out to VLN, like so. And I can use equation 1 from earlier today to express all of those inductor voltages in terms of the current that's flowing through that series combination of elements. So that would look like L1 times the derivative of I with respect to time plus L2 times the derivative of I with respect to time all the way out to L sub n times the derivative of I with respect to time. So there's a common factor of di by dt in all of these terms. So I can effectively take that part out and it leaves behind. Actually, let me do it like this. L1 plus L2 all the way out to L sub n, like so, di by dt. And from here, we can essentially say that this guy right here is just the equivalent inductance, right? So essentially, whenever we see inductors in series, they simply add together just like resistors. So I'm going to write that part down. Inductors in series combine like resistors in series. And now, without doing any derivation or calculus whatsoever, I would like for one of you to make an educated guess as to how inductors in parallel are going to behave.
Same way as resistances in parallel.
Exactly right. So inductors in parallel combine like resistors in parallel. We could mathematically do it and we'd have a bunch of integrals and all of that kind of stuff added together. That's gross. I don't want to do it. You guys are, I'm sure, tired of listening to me talk about circuits for 90 minutes straight. So let's just say inductors in parallel combine like resistors in parallel. And call it a day. So that is the last thing that I wanted to talk about for today. So couple of things. First, I have pushed back the due date for homework set number 10, I believe, until Friday or something like that. Maybe even Saturday. I honestly don't remember at this point because I didn't get the lecture video uploaded until earlier today because I just totally forgot about it. So I apologize for that. So I pushed back the due date for the ICA and the homework to accommodate for that. I will be around. Um, if you guys need any assistance with your homework or anything, please just shoot me a text or shoot me an email, and I'd be more than happy to help you. The other thing I wanted to mention is that it is the 4th of July weekend, so we don't have any class on Friday. I hope you guys stay as safe as you can with fireworks and all of that kind of stuff involved. Hopefully, you all return from the miniature break with the same number of fingers and toes that you currently have. So anyway, I hope you have a good rest of your afternoon. I'll stick around on Zoom if you have any questions or anything. And if not, again, have a happy and safe 4th, and I'll see you on Monday.